frequency very, very subtly in such a way that it's incredibly difficult to distinguish from random genetic drift. So I would argue that we really want a full picture of polygenic adaptation through short timescales from genomic data, but we're lacking it in a few ways. Specifically, how much of genome-wide variation is affected by polygenic adaptation? Second, you can look at a very quick shift in an optimum, such as this peak shape here, and we wouldn't be able to detect this kind of shift from genomic data alone currently. Additionally, we also want to understand what time scale selection acts over, whether it's tens to hundreds of generations. So what I hope to convince you of today is that temporal data offers a very unique way to answer these questions. So the work that I'm going to be explaining today differs a little bit from what I'll call the classic temporal selection scan, where here the goal is to discover selected loci by looking for a signal of allele frequency changes that change too quickly to be determined by random genetic drift alone. In contrast, our approach is a bit different. And what it's doing is it's sort of modeling all genome-wide allele frequency changes to tell us something about evolution that's ongoing in the population. And the signal that we're using is a bit different as well. What we're doing is we're modeling the covariances and neutral allele frequency changes through the generations. So to sort of give you an idea of how this is working, you can imagine a neutral allele trajectory from some initial generation 0 to some later generation t. And the total change over the time course of this experiment is 0 to t, and the allele frequency change is pt minus p0. So you can think about the variance in allele frequency change here as being the variance of a sum of lots of little changes, either between adjacent generations or adjacent time points. Now, under neutrality, we can further simplify this by writing this as the sum of a variance of all these individual changes here. However, something special happens with selection, and that is that there are now covariances between these allele frequency changes through time. So to sort of give you an intuition about how these covariances are created, I want you to imagine a neutral allele here, colored in orange, that happens to find itself on a beneficial blue background. So at some time point I, given that this neutral allele is on this beneficial background, you would expect a positive change in allele frequency. And as long as some fraction of the neutral alleles in the population remain on this beneficial background at a later time point j, you also expect delta pj to be positive. And this acts to create positive covariance in allele frequency change. And with temporal data, we can go out in a population looking across the generations and measure the allele frequency changes and actually directly calculate these covariances. So we have a preprint that's on bioRxiv now. If you want to understand the mathematics of our method and theory, I suggest that you go take a look at this. For the most part, I won't be talking about the mathematics of the method here. What I'll be focusing on instead is how we measure this signal in real populations. So what we do is we sort of, with genome-wide allele frequency changes, calculate an empirical variance-covariance matrix, in this example here, over 6 time points. And you can imagine writing the variation in allele frequency change from some initial generation 0 to some later time point t as, in the case of neutral evolution, the sum of the variance of all the changes, which in the case of this variance-covariance matrix is the sum of all these diagonal variance elements. In the case where there's selection operating, we expect these off-diagonal covariance elements to now no longer be 0. And we can express sort of the magnitude of the effect of linked selection in the population as this term here, which I call G, which is essentially the sum of all these covariance terms on the off-diagonal divided by the total variation in allele frequency change. So just to reiterate, this is the proportion of total variation in allele frequency change driven by linked selection. In the case of neutrality, we expect this to be 0, and if there's selection that's ongoing, we expect it to be greater than 0. So what do we see when we look at some real data sets? I'm going to start with this example this paper by Bargay et al., which looked at software simulants evolved in a novel lab environment over 60 generations. What's really neat about this experiment is that there are 10 replicate populations, and they've sequenced them at 6 different time points. So what do we see with the covariances here? Well, what I'm going to be doing is plotting the rows of the variance-covariance matrix here. And what this is doing is it's holding a particular reference time point and looking at the covariances as they change through later time points with respect to this reference time point. So looking at the first row of covariances, you can see that they're overall positive, and then through the generations, they decrease and they actually become negative. So looking at the second reference time point, you see a very similar pattern, and this is all indicative of linked selection operating in this population. Same thing with the third reference time point. And then finally, the last two time points show weaker covariances. So what does this translate to in our metric G? I'm going to be plotting this metric G on the y-axis here, through time on the x-axis. By that I mean I'm going to be looking at different subsets of the variance and covariance matrix through time. And because this is a replicate sort of population experiment, I'm going to be plotting each of these replicate populations measures of G in these different colored lines, and then the across replicate average G as this gray line. And what you see is that through time, the cumulative effect of link selection grows. And over the course of the experiment, across all replicates, we see just under 10% of the proportion of variation in allele frequency change is driven by link selection. And in some of these cases, it's up to 20%. And I should say at this point, because of the way I've designed this estimator and the nature of this experiment, this is actually much closer to a lower bound than an unbiased estimator of the true proportion of link selection that's affecting variation in allele frequency. So I want to point out something about this earlier picture, and that's these negative covariances right here. So our theory suggested that negative covariances could be created by a reversal in the direction of selection. So we were thinking that this could be something that indicated that. So to look at this in more detail, what we've done is rather than averaging across the entire genome, we've sort of binned the genome up into tiny windows and calculated the covariance in each one of these windows. And what we find is that you see in earlier time points sort of regions where there's positive covariances here and here, which could indicate that there's a lot of adaptive variation in that particular region of the genome. But later in the experiment, you see these regions that sort of indicate negative covariances. And we have to be a little bit careful here. Because we're averaging over fewer loci, we're at risk of sort of interpreting sort of sampling noise as which could create negative covariances by chance under a pure drift model. So to address this limitation, what we've done is taken all of the sort of covariances across the genome, and we've plotted them, a distribution of them. And we compare this to an empirical null distribution that we would see under neutrality. And the way we generate this null distribution is we sort of randomly flip all of the signs of the allele frequency changes and then recalculate the covariances. And because neutral evolution is a directionless force, this acts as a very conservative empirical null distribution of the process that we would expect the covariances that you would see under this process. So what do we see? So if you look at the covariances 2 generations apart, we sort of saw the picture that we saw earlier, which is this excess positive covariances here. However, if you look further in the experiment, you see that there's an excess of negative covariances, indicating that there is a signal of the direction of selection changing. And I should emphasize here, this is not something the designers of the experimenter planned. This is something that this method is revealing about the population that we didn't know a priori. So I'm going to talk about another evolutionary sequence study in Drosophila simulants. This one was done by John Kelly and Kimberly Hughes. And the design of this is similar. There's 3 replicate populations. But the limitation here, the difference here is that there are now 2 time points. So we've had to adjust our methods to accompany this. So what we've done is we've developed a very similar approach, which are these between replicate covariances. And so what these are getting at is a signal of convergent selection pressure across these replicate populations. And so you can imagine the case where there's no convergent selection pressure. These covariances, between replicate covariances, will be 0 in expectation. In contrast, if all of these replicate populations show a signal of convergent selection pressure, we would expect these covariances to be positive. So looking at this Kelly and Hughes data for these 3 replicate populations, what I'm going to do is plot the covariance on the y-axis for each of the pairwise comparisons of the replicate populations. And across the board, we see a signal of link selection. And if we were to modify or measure G for this between replicate design, what we see is that greater than 25% of the variance in allele frequency change is due to link selection. So the last study is this really nice work done by Castro et al. That's coming out in eLife very shortly. And this is an artificial selection experiment done in mice, where they've selected for tibia length, controlling for body size. And over the course of 20 generations, they've seen across these 2 selection lines, which they've named Longshanks 1 and Longshanks 2, roughly a 5 standard deviation shift in the mean phenotype. And what's really nice about the study design is that they have a control line, which undergoes no selection, that we can compare to these other 2 lines. And what we find is that when we compare the control line to the Longshanks line, we see no signal, as we would expect, of convergent selection pressure. Similarly, when we compare the control line to Longshanks 2, we also see the same signal, or lack of signal, I should say. And then finally, when we compare the two Longshanks lines, we see a signal of selection as we would expect. So I want to sort of conclude, hopefully I haven't spoken too quickly, I want to conclude on a really interesting analysis that I just did yesterday, so I don't have any slides to reflect this, I apologize. So what happened was I got in contact with the authors, and they've been really wonderful providing feedback on this. And they suggested that we remove two major effect loci that their method turned up. These loci were the two sort of outliers in their analysis that were common between these two Longshanks lines. And they were worried that we were potentially reading too much, or sort of gathering too much information from these two major effect loci, and that was affecting our covariances. We weren't really picking up sort of a polygenic signal. And so I took an approach that was rather conservative. And what I did was I removed not just those two loci, but the entire chromosomes that they were on, simply because we didn't really understand the extent of LD in this population. And what was remarkable is that after doing this, we found that the covariances didn't change at all. The picture is pretty much the exact same. So I'll conclude on the note that I think what this method is doing is potentially truly picking up on polygenic adaptation over very short timescales in a way that can elucidate things like changes in the direction of selection without any a priori knowledge that that's happening in a population. With that, I would like to thank these folks, and I'm happy to take any questions.
So I guess I have two. One is the effective linkage. So you showed me the couple of plots, and the peaks are right around the centimeters, right? So how does your method sort of reflect variation in LD across the genome? And then the second question, which might be related, is how does sort of differences in the allele frequency spectrum of the adaptive alleles themselves affect the power of the genome?
Those are really good questions. So to answer the first question, our method really relies on the signal of LD, and one of the things we've done in other cases is we've looked at the relationship between the covariances and the combination range covariances and linkages. And it's rather unfortunate that there were these great quality sequence studies in simulants. Unfortunately, these studies lack LD maps that are reliable. I think the best recombination map has rates per whole chromosome are from the 70s or something. So this is something that, with really good recombination maps, with really good knowledge of LD in an experiment, the preprint that I linked to earlier actually suggests that we can estimate VA through time without information in these populations. So we haven't been able to do that in anything with simulation data, mostly because of the limitations of current evolving sequence studies. With respect to your second question, there is an issue there with allele frequency. And really, the issue there is that the variance in allele frequency change is driven by essentially the heterozygosity. So we sort of remove that effect and do a variance stabilizing transformation. So I don't have time for the questions, but I'm happy to have time later to chat.